Hello everyone and welcome to our channel MooTechie. It's wonderful to have you with us today as we dive into the fascinating world of chemistry. We're going to explore the essential concepts of oxidation, reduction, and redox potential together. So get comfortable and let's begin our learning journey. Let's start by understanding what oxidation is. Oxidation is defined as the loss of electrons. A handy way to remember this is with the mnemonic LEO, which stands for loss electrons oxidation, or OIL, meaning oxidation is loss. Oxidation also involves an increased oxidation state, meaning the oxidation number of an element goes up as it loses negative charge. Historically, it was defined by chemical changes, like gaining oxygen or losing hydrogen atoms. And importantly, oxidation reactions often release energy, which we call exergonic, especially in biological systems. Here's a great example for you. Iron metal undergoes oxidation. An iron atom loses 2 electrons to become a ferrous ion. So we write that as Fe becoming Fe2 plus 2 electrons. This is a fundamental part of understanding redox reactions. Now let's move on to the flip side of the coin, reduction. Reduction is the gain of electrons. You can remember this with GER for gain electrons reduction, or RIG, which means reduction is gain. This process involves a decreased oxidation state, where the oxidation number reduces as the species gains negative charge. Chemically, it often involves losing oxygen atoms or gaining hydrogen atoms. And it leads to a charge reduction, where positive ions become less positive or neutral, and neutral atoms can become negative ions. For instance, a copper ion gains 2 electrons to become a copper atom. We write this as Cu2 plus 2 electrons yields Cu. These two processes, oxidation and reduction, are the core fundamentals of redox chemistry. As we continue, let's understand how these two processes are linked through electron transfer and redox pairs. Electrons move directly from a donor species to an acceptor species. They don't just float around freely in solution. The reductant is the donor. It donates electrons and gets oxidized. The oxidant is the acceptor. It accepts electrons and gets reduced. Together they form what we call conjugate redox pairs, like the Fe2+/Fe3+ pair. It's crucial to remember that oxidation and reduction are inseparable half reactions. They always occur together in a coupled process. Visually, we often represent this with a donor labeled red, losing electrons, and an acceptor labeled ox, gaining them. The general mechanism is simply reductant plus oxidant yields products. Next, we explore some common redox pairs found in nature and our bodies. We have metal ion pairs like Fe3+/Fe2+ and Cu2+/Cu+, which are common in redox enzymes such as cytochromes. Then we have the oxygen/water pair, which is the ultimate electron acceptor in respiration. The reaction is XO2 plus 2H plus 2 electrons yields H2O. We also have biological carriers like NAD+/NADH and FAD/FADH2, which carry electrons from fuel molecules to the electron transport chain. These conjugate redox couples are written as oxidized/reduced, and the potential difference between them is what drives electron flow. To visualize this, imagine a redox ladder. At the top, with a high redox potential around 0.82 volts, we have the O2/H2O pair, a strong acceptor. Further down the ladder, we have pairs like cytochrome C, succinate/fumarate, and NAD+/NADH with potentials around 0.25, 0.004, and 0.32 volts respectively. At the very bottom, around -0.42 volts, we have the H+/H2 pair. The key takeaway is that electrons flow spontaneously from a negative potential to a more positive one. Coming up, we'll discuss the agents that drive these reactions, oxidizing versus reducing agents. An oxidizing agent accepts electrons and gets reduced. Its oxidation number decreases. Examples are O2, MnO4-, and NAD+. On the other hand, a reducing agent donates electrons and gets oxidized. Its oxidation number increases. Examples are H2, Fe2+, and NADH. In a simple diagram, you'd see the oxidizing agent gaining electrons and the reducing agent losing them. This is the heart of electron transfer. Now let's understand the force behind this flow, the redox potential, also known as EH. The standard reduction potential measures a chemical species' electron affinity, its tendency to acquire or lose electrons. It's measured in volts with the standard hydrogen electrode, or SHE, as our 0.00 volt reference. A positive EH value indicates a strong oxidizing agent like oxygen, which loves to grab electrons. A negative EH indicates a strong reducing agent, which wants to donate electrons. For example, the 2H+/H2 pair is at 0 volts. NAD+/NADH is at negative 0.32 volts, and ferredoxin is at negative 0.42 volts. Electrons always flow from a more negative to a more positive potential. Moving forward, we'll see that EH isn't fixed. It's affected by several factors which we describe using the Nernst equation. The primary driver is the ratio of oxidized to reduced species. A higher concentration of the oxidized form increases the potential, making it more positive. EH is also pH dependent, and since protons are often involved, biochemists use E0', which is the standard potential at pH 7 instead of pH 0. Temperature and ionic strength also play a role, affecting the energy term and the effective concentration of ions. The Nernst equation is written as EH equals E0' plus RT over N times the natural log of the concentration of oxidized over reduced. E0' is the standard potential at pH 7. The RT over N part is a slope factor that depends on temperature. At 25 degrees Celsius, this slope is approximately 59 millivolts per decade change in the ratio divided by N. Let us now look at why EH is so significant in biochemistry. Firstly, it guides electron flow. Electrons move spontaneously from carriers with lower, more negative EH to those with higher, more positive EH. It also regulates metabolism. The ratio of oxidized to reduced cofactors like NAD+ to NADH controls the activity of key metabolic enzymes. Furthermore, it drives ATP production. The large EH difference between NADH and O2 in the electron transport chain releases free energy, which is used to synthesize ATP. Finally, it helps maintain the cellular state, providing the right intracellular redox environment for protein structure and antioxidant defense. A diagram of the electron transport chain shows this beautifully. It starts with NADH at negative 0.32 volts, then electrons move through complex 1 and other carriers like ubiquinone and cytochrome C with potentials around negative 0.2, 0.05, and 0.25 volts, finally reaching oxygen at positive 0.82 volts at complex 4. Energy is released at each step as electrons flow spontaneously from NADH to O2. Following this, you'll notice we can actually measure this potential. Measuring EH, or redox potential, uses a special electrode setup. It involves a platinum working electrode, which is sensitive to electron transfer, and a stable reference electrode, like a silver/silver chloride electrode. The biological range of EH is vast, spanning from around negative 320 millivolts for strong reductants like NADH to positive 820 millivolts for strong oxidants like oxygen. A higher positive EH indicates an oxidizing environment, while a lower negative EH indicates a reducing environment. These values are typically reported relative to the standard hydrogen electrode. In a typical setup, a PT electrode and a reference electrode are placed in the sample solution. A potentiometer measures the potential difference between them, giving us the EH value. Finally, let's wrap up with a summary and the key takeaways. Remember the fundamental definitions with oil rig. Oxidation is loss, reduction is gain. They always happen together. Reductants are the donors that transfer electrons to oxidants, the acceptors, and this drives the flow of chemical energy. Redox potential, EH, measured in volts, tells us the direction of this flow. A positive EH attracts electrons, meaning it's oxidizing, while a negative EH donates them, meaning it's reducing. Think of it as a continuous cycle. Oxidation involves losing electrons, reduction involves gaining them, and together they form a redox reaction that powers so much of our world. Thank you for joining me in exploring these fundamental concepts. I hope this has been a clear and engaging lesson for you. Thank you.